Hey, hello everyone. Welcome to episode 77 of our Warsaw Quantum Computing Group meetup. My name is Pavel. I will be the moderator today. And today we host another great speaker, Grzegorz Czelusta, a PhD candidate from Jagiellonian University in Krakow. And he will give a talk titled Quantum Computing for Quantum Gravity. Sounds interesting. Before we start, I would like to thank our strategic partners for supporting us: Sonovero R&D, Quantum.io, Onyx, QLab, ThinQubit, and Cogit, and our honorary partners. So there are more than 10. So I will just show the slide to thank them for advertising our events and supporting the organization. And just two more announcements. So as you can see, this meeting is recorded. So hopefully we'll later publish the video to at our YouTube channel. And if you have any questions, you can post your questions on the chat, or you can raise your hand. We can try to interrupt if there's an opportunity. Grzegorz, is it fine for you to
Yeah,
turn this
is
meeting
it fine?
interactive?
But I want to see the
Yes. So I
probably
will.
the
I will try
hands. So
to.
yeah, so you
Yes.
can interrupt me. Yeah,
Yes,
yeah.
I will try to interrupt if needed, and anyway, there will be a dedicated Q&A session at the end. So with this, I will stop sharing my slides, and Grzegorz, thanks for accepting our invitation. It's our pleasure to have you with us for the first time, as far as I remember. So the Zoom is yours, and we can start.
Thank you, Pavel, for invitation and for introduction. Yeah. Today I would like to talk about applications of quantum computing to problems motivated by quantum gravity. So first, what is quantum gravity? Quantum gravity is often described as the missing theory that should connect two extremely successful frameworks, classical gravity, and which is described by general relativity, and quantum mechanics, which governs physics at microscopic scales. So there are several candidates approaches to quantum gravity, but so far we do not have decisive experimental evidence that would allow us to choose between them. There is even the logical possibility that quantum gravity in the usual sense is not needed, or that the correct description will look very different from our current expectations. Um, in this presentation, I will focus mainly on spin networks that appear in several approaches to quantum gravity, in particular in loop quantum gravity. And my goal is not to give, of course, the full introduction to loop quantum gravity, but rather to explain why spin networks arise and what their quantum geometric interpretation is, and how they can be represented and simulated using quantum circuits on quantum computers. So let us first step back and ask, what is quantum gravity? What is quantum gravity supposed to combine? The first ingredient of quantum gravity is gravity, and the most accurate theory of gravity that we currently have is Einstein's general relativity. It is a classical theory in which gravity is not described as a force in the usual sense, but as the curvature of spacetime. And the Einstein equations relate the geometry of spacetime to the distribution of matter and energy, and in a very compressed form, we can say that the matter tells spacetime how to curve, and the spacetime tells matter how to move. However, general relativity also comes with deep conceptual problems. One of them are singularities. Okay, here are have another animation which show that general relativity connects geometry of space-time with distribution of matter and energy. and this connection is described in Einstein's equations. Um, and this theory is one of the best experimental verified theories. For example, when you have GPS satellites, then the dilatation of time, uh, which means the difference in speed of time close to the Earth and on some orbit where there is satellite, is very different. And this differences in speed of time, let's say, can be measured very accurately, not only between Earth and orbit, but also in laboratory between a difference in levels above ground, like 10 centimeters. So this theory is very accurately tested. But there are some problems in this theory. One of them is a prediction of singularities, regions where curvature becomes infinite and the classical description breaks down. We do not know whether such singularities are physically real or whether they are just artifacts of applying a classical theory beyond its domain of validity, where quantum effects should become important. The best known examples of singularities are the initial singularity of the universe, the Big Bang, and the singularities inside black holes. A black hole forms when a sufficiently large amount of mass or equivalently energy is concentrated in sufficiently small region, and around the singularity an event horizon forms, which prevent us from directly observing the interior of black holes. Uh, and this particular aspect of general relativity would be important to justify why we need quantum gravity. So we have general relativity, and now let us look at the second ingredient, namely quantum theory. And one of the characteristic features of quantum mechanics is uncertainty principle. The more precisely we know the position of particle, the less precisely we know its momentum, and vice versa. So when we decrease uncertainty of position of particle, we increase its momentum and therefore its energy. So we can try now imagine that we want to probe a very small region of space. So we have some point in space, and we want to resolve shorter and shorter distances. And to do this, we need to use higher and higher energies. But at the same time, this energy itself gravitates. Yeah, as we know, energy or equivalently matter gravitates. It curves space-time. So as we zoom in farther and farther, the energy required to probe the region increases, and the curvature generated by that energy also increases. So eventually, the region we are trying to observe would be hidden behind the horizon of newly formed black hole. So it means that when we combine classical gravity with quantum mechanics, there is some fundamental minimal distance below which we cannot observe space. And this distance is known as the Planck length, and it is very, very small. So there are no experiments currently which can probe space at such small distances. But we see that at these distances, probably there is some fundamental disagreement between classical gravity and quantum mechanics. And this is one of the simplest arguments to make to justify existence of quantum gravity. This argument was already made by Matvei Bronstein in 30s, so quite a long time ago. Matvei Bronstein was Soviet physicist who was killed by NKVD during Great Purge. So he died in quite young, quite young. But he as first observed this disagreement between classical gravity and quantum mechanics. So this is one of the reasons why quantum gravity may be necessary for complete description of physical reality. And one of the candidate theories of quantum gravity is loop quantum gravity. And I will now briefly outline how the quantization of general relativity leads towards the structures used in LQG. So classical general relativity can be formulated in the Lagrangian formalism by defining the action. So this is the action, the integral of Lagrangian for classical general relativity without matter. And applying the variational principle to this action, we obtain the Einstein equations. So it is equivalent to Einstein equations, which describes this connection between curvature and distribution of matter energy. However, we can also perform a standard transition from the Lagrangian formalism to Hamiltonian formalism. And in general relativity, this requires the so-called ADM formalism. In this formulation, we take our four-dimensional spacetime and we decompose it into three-dimensional spatial hypersurface of constant time, which evolve in time. So now we have three-dimensional spaces which evolve in time. And to describe this evolution of space in time, we need to introduce so-called lapse function and vector and shift vector. And these two objects, roughly speaking, they tell us how consecutive spatial slices are related to each other. And this is some technical trick, but this allows us to write the Hamiltonian formulation of general relativity. So this is the Hamiltonian of gravity for vacuum. There is no matter, but we can add also matter term if you want. And this Hamiltonian has a very special structure. It is a sum of constraints. In ADM formulation, we have the vector constraint and the scalar or Hamiltonian constraint. This HA is vector constraint and H is scalar constraint. And this is a situation specific to gravity. And for physical configurations, which means configurations satisfying the constraints, the Hamiltonian vanished identically. So this is a strange situation because for physical configurations, Hamiltonian is identically equal 0. And this fact, this reflects the fact that in general relativity, time evolution is deeply related to gauge symmetry and space-time diffeomorphism invariance. In other words, time evolution in gravity is not a real evolution, but it is a kind of gauge symmetry. So this is typical for gravity systems. But so far we are still in the classical regime. And before we move to quantization of this formalism in spirit of the LQG, we need to first introduce a new set of variables, the Ashtekar-Barbero variables. I will not go into the technical details here. The important point is that these variables are based on SU2 gauge structure, and that general relativity can be rewritten in terms of them. And in these variables, the Hamiltonian is still sum of constraints, but now there are three types of constraints: the Gauss constraint, GI, a vector constraint, HA, and a scalar constraint, H. The Gauss constraint appear here because when during the introduction of Ashtekar-Barbero variables, we also introduce tetrad-like variables, and they introduce an internal gauge freedom, and the Gauss constraint is needed to enforce invariance under local SU2 gauge transformations. So we have Hamiltonian expressed in variables that are well suited to quantization. And now we can proceed to the quantization. And since we are dealing here with a constraint system, we follow Dirac's procedure for quantizing constraint systems. First, we replace the classical constraints with quantum operators. Then we need to define kinematical Hilbert space on which these operators act. And finally, solving the constraints means finding those states from kinematical space that are annihilated by the constraint operators. And these states form the so-called physical Hilbert space. So this is the general procedure for quantization of constraint systems. And now we can take a look how it looks in construction of LQG. And this will naturally lead us to the notion of spin networks. So we have introduced Ashtekar-Barbero variables, which are fields defined on space. And these fields describe geometric degrees of freedom of space. So imagine a path in space. Along this path, the connection A takes different values, and we can integrate this connection along the path and then exponentiate it. And in this way, we obtain an object called a holonomy. It is an element of the SU2 group, and it is very convenient variable to use in the quantum theory. So now, instead of describing geometry directly by fields defined at every point of space, we can probe space using a network of paths. And to each path or link, we can assign a holonomy that is an element of SU2 group. And then the function defined on such graph, depending on the holonomies assigned to links of this graph, is called a cylindrical function. The space of all such functions for all possible graphs forms a kinematical Hilbert space of LQG. And the mathematical details, which I am omitting here, are made precise by the Ashtekar-Lewandowski construction. The many aspects of rigorous mathematical formulation of this Hilbert space was done by Jerzy Lewandowski from Warsaw, who passed away 2 years ago. But we don't want to dive here into the technical details. We arrive In this way, we arrive at the description of spatial geometry in terms of graphs whose links carry SU2 holonomies. And this is the starting point of spin networks. And at this stage, you can ask where do the spins in the name of spin networks come from? And I will return to that in a moment. You can see probably that there is SU2 group, so this is the origin of the spins. But it is also now worth to emphasize that spin network techniques are not used only in LQG, but they also appear in many related approaches to quantum gravity and quantum geometry. So this tool can be used in many formulation of quantum gravity. And once we have defined kinematical states, we can start applying the constraints. And as I mentioned, in the Hamiltonian formulation of gravity, we have three constraints: Gauss constraint, vector constraint, and scalar constraint. And in this presentation, I will focus on the implementation only of the Gauss constraint. Implementation of the vector constraint is in a sense almost free once we work with graph structures, because application of vector constraint HA it corresponds to introducing equivalence classes of graphs, and two states are considered equivalent if their graphs are related by special diffeomorphism. So basically, if two graphs are equivalent as a graphs and equivalent as nodes, then we consider them as equivalent states. And this is basically the application of vector constraint. There is also third one, scalar constraint, H. And this is much more difficult, and its full implementation is one of the technically hardest and conceptually deepest part of LQG, and I will not discuss it here at all. So let us therefore focus on the Gauss constraint. The Gauss constraint means that the cylindrical function defined on the given graph must be gauge invariant. In other words, if the holonomies entering this function are transformed by SU2 group elements, the value of the function should remain unchanged. And since the gauge transformation of holonomy living on a link acts at the endpoints of that link, the Gauss constraint is imposed at the vertices of the graph where several links meet. So now we can return to the origin of the spins in the name of spin network. Spin network states, as we see, are functions on products of SU2 groups. So we have one copy of SU2 group assigned to each link of the graph, and by the Peter-Weyl theorem, this space of functions can be decomposed into irreducible representations of SU2. So we can decompose this space of functions to tensor product over links of graph, and tensor direct sum over spins. It means over representation of SU2 elements. And then each link can be decomposed into a tensor product of two Hilbert spaces for spin J. So this means that we can describe each link of the graph equivalently as a pair of spins. So we have some link labeled by holonomy H. We choose some representation of this SU2 holonomy, which is labeled by spin number J. And then we can equivalently describe this link as a state, which is a state of pair of spins J, and the coefficients in this state are elements of this holonomy, of this SU2 element. And when the holonomy is unitary, then this state corresponding to this holonomy is a maximally entangled state. So we may think now about links of spin networks as a maximally entangled pairs of spins. So now we can move to consideration of vertex of spin network. So we have vertex of the graph where several links meet. And in the spin interpretation, this means that several spins meet at the vertex. And the Gauss constraint that then tell us that the state associated with the vertex must be SU2 invariant. And in my work, I focus mainly on the case where all spins on the links are equal to 1/2. This means that all holonomies are taken in the fundamental representation of SU2. And I also restrict attention to only 4 regular graphs. So graphs where every vertex has valency 4. And this is the simplest non-trivial case for spin networks. And at the same time, it is very convenient for simulations and interpretation. So let us focus on the implementation of Gauss constraint for 4 spins 1/2. We know that tensor product of 4 spins 1/2 can be decomposed into irreducible SU2 representations as follow. It contains 2 copies of spin 0, 3 copies of spin 1, and 1 copy of spin 2. And imposing the Gauss constraint means selecting the SU2 invariant part of this space. So it means that we choose only the spin 0 subspace. And we see that there are 2 spin 0 subspaces. So it means that the state of the 4 spins at vertex is, after projection onto this spin 0 subspace, is state living in 2-dimensional space. So this is crucial observation, since the invariant subspace is 2-dimensional, and since this is 2-dimensional subspace, it means that nodes of a spin network can be represented by qubits. And diagrammatically, we can indicate this by adding an extra leg at the vertex. So each vertex can be viewed as a tensor with 4 indices associated with the incident links and 1 internal index corresponding to the invariant degree of freedom, inner degree of freedom of the node, let's say. And this tensor is called the Wigner 4J symbol. And for arbitrary spins on the links, not necessarily equal to 1/2, but arbitrary J spins, the dimension of the invariant space of vertex is determined by the allowed recoupling channels, and it is given by this formula. And when we focus on our special case of 4 spins 1/2, we obtain exactly two-dimensional vertex space. So this is why this case is particularly attractive from the point of view of quantum simulations, because both the spin degrees of freedom living on links and the gauge invariant degrees of freedom at vertices can be encoded using qubits. So now let us return to the geometric interpretation of spin networks. Recall that spin network states were introduced here as a quantum state of spatial geometry. Therefore, the links and vertices of the graph should have some geometric meaning. And take 4 spins meeting at a vertex and think of them as vectors that sum to 0. By Minkowski theorem, a set of vectors satisfying a closure condition uniquely determines a polyhedron. So these 4 spins uniquely determine tetrahedron in our case. And the vectors corresponding to spins define the outward normals to the faces of the polyhedron, while the lengths determine the areas of these faces. And in this sense, spins and therefore links of the spin network correspond to quantized surface areas. I am presenting here this only at the intuitive level, but this statement can be made precise, and one can define an area operator in LQG and show that spin network states are eigenstates of this operator, and the corresponding eigenvalues are determined by the spin labels on the links. So the links are associated with this discretized area. And similarly, the state associated with a vertex after imposing the Gauss constraint has an interpretation related to the volume. One can define a volume operator, and spin network states are eigenstates of this operator as well. And we obtain also discrete spectrum of this operator. So each node, each vertex of spin network carries a quantum of volume, and each link carries a quantum of area. And also, these links carrying areas tell us how the elementary chunks of volume are glued together in the spin network. So, for example, consider 2 tetrahedra glued along one of the one common face, and the shared face corresponds to internal link connecting two vertices, and the remaining 6 faces form the boundary of the total region of these 2 tetrahedra. Thus, the corresponding spin network is so-called open spin network. It has 2 vertices, one internal link representing the common face, and 6 external links representing the boundary faces. And therefore, by generating the spin network states, we are generating basically quantum states of geometry. And by constructing sufficiently complex spin networks, we can represent larger, possibly macroscopic regions of space, including information about their curvature, topology, and boundary structure, and so on. And it is also important to note, once again here, that in this formulation, the discreteness of areas and volumes is not imposed by hand, but it appears as a result of quantization. Okay, so we have some basics of spin networks. established, and now we can move toward quantum computing. Okay, we try to build some larger graph, namely graph on 6 vertices. So we have 12 links carrying holonomies. We can think of them as having 12 pairs of spins. And after imposing the Gauss constraint, we obtain 6 qubits representing the 6 Gauss invariant vertex degrees of freedom. And as I discussed earlier, each link corresponds to pair of maximally entangled qubits. And for trivial holonomies, these are singlet states. So such pairs can be generated by simple quantum circuit. And so this circuit generates a singlet state of 2 qubits corresponding to this trivial holonomy, link with trivial holonomy. And to generate a larger spin network state, we first prepare entangled pairs of qubits corresponding to the links. So we have a first link, second link, third link, and fourth link. And then we apply a projector onto SU2 invariant subspace at each vertex. So at each vertex, at each 4 qubits, which are in given vertex, we apply a projection operator. And the explicit form of this projector as a quantum circuit can be found in my paper, in this paper. And this method allows us to construct quantum states of arbitrary 4-valent spin networks with spins 1/2 on the links. However, this method also has some disadvantages because for network with n spins, with n vertices, it requires 4 times n qubits, and it requires post-selection on 3n qubits. So this makes the method costly for larger networks because this projector W is not unitary operator, of course. So we need to post-select some qubits at the end. And for this reason, I later formulated another approach, which is inspired by tensor networks techniques. And as I mentioned before, each vertex of spin network can be treated as a tensor with 5 indices. 4 indices associated with links and 1 internal index corresponding to the Gauss invariant vertex degree of freedom. And now we introduce an orientation on the links. And this orientation corresponds to whether an index appears in upper or lower position in the Wigner-Forsyth tensor. So we can think of the vertex tensor as having incoming and outgoing links, and this extra link corresponding to internal degree of freedom. And then we can construct a quantum circuit corresponding to this tensor. Such circuit has 2 input qubits, 2 output qubits, and 1 extra output qubit corresponding to the internal degree of freedom of the vertex. And while this tensor is not unitary, the circuit requires additional ancilla qubits initialized in 0 state and post-selected back onto the 0 state. And for each possible combination of incoming and outgoing links, so lower and upper indices, we can prepare dedicated quantum circuit, and the explicit construction of all of these circuits is given in this paper. And using this tensor network inspired construction, we can generate spin network states more efficiently. Namely, before I move to the complexity, now there is one remark. To use this method, we need to assign orientations to the links of the spin network, but it is quite easy because changing the orientation of link corresponds to replacing the holonomy carrying by this link by its inverse. So the orientation of links can be adjusted to match the circuit construction. We just need to use inverse of holonomies everywhere where we need to change this orientation of link. Okay, so now the comparison between the complexity of this method and previous one is following. Instead of 4 n qubits, where n is number of nodes of spin network, instead of 4 n qubits for previous method, this method required a number of qubits which lies in the range between 2n plus 1 and 2n plus n over 2 qubits, depending on the structure of the graph which we want to simulate. And here I have some example of generating spin network state on real quantum hardware. Here I show the generation of 5 vertex spin network, and this plot compares the probability distribution over computational basis states obtained from the quantum processor and distribution obtained by theoretical computations. And these results were generated on the IBM FES processor. The green bars corresponds to theoretical probabilities. Blue bars correspond to experimentally obtained probabilities. This was just some simple test that I performed yesterday. There is no error mitigation, no additional optimization, so there is room for improvement. But still, in the simplest setup, the fidelity of the fidelity between obtained distribution and theoretical distribution is around 93%. But of course, this is classical fidelity. It compares only probability distributions. The full quantum fidelity, which would compare the complete density matrices of the states, would be lower. In aerial tests on older IBM processors that I made, the quantum fidelity was around 60 something percent. So now let me emphasizing two main benefits of representing spin networks as quantum circuits. The first benefit is the possibility of simulating larger spin networks, which may be relevant to study the semi-classical limit of LQG. Because when we look for the theory of quantum gravity, we want to have a theory which in semi-classical limit gives the same results as classical gravity. And now using standard numerical methods, we can generate spin network states with up to a few dozen vertices. But to study the semi-classical limit, we would like to go significantly beyond that. And the analytical methods, on the other hand, that are used to research on semi-classical limit, usually focus on the large spin limit for graphs with relatively small number of vertices. So using quantum simulations allow us to make limit not for large spins, but for large number of spins, kind of thermodynamical limit. Uh, so, but there is also the second benefit, namely the possibility of studying the quantum information structure of spin networks. This is increasingly active area of research, um, where one tries to reconstruct spatial geometry from the structure of quantum entanglement. And having explicit quantum circuits that represent quantum stage of geometry may be useful in this context. One of the concrete realizations of this idea is the so-called bulk boundary map. This is a map connecting bulk degrees of freedom with boundary degrees of freedom. And it is inspired by holographic ideas. And as I showed earlier, we can consider a region of space with a boundary. For example, we can take two tetrahedra, glue them along one common face, and then the bulk is represented by two vertices. The bulk is represented by two vertices, so by two qubits. And the external boundary is represented by 6 links, so by 6 boundary qubits. And we can therefore construct a quantum circuit that maps the two bulk qubits into six boundary qubits, into the 6 boundary qubits. And the construction of this circuit can be written explicitly. Here we have a circuit which use two blocks which are explicitly known how to be constructed. It is in our paper. And this circuit takes two input qubits corresponding to bulk degrees of freedom, to volume, let's say, and it outputs 6 qubits corresponding to boundary of this region, to the area which is around this volume. And this is some concrete realization of abstract idea of bulk boundary map, which can be used in simulations, but also in some analytical derivation of properties of this map. Okay, so to conclude, here is a list of our papers on the simulations of quantum gravity inspired systems using quantum computers. Three of them directly related to the spin network constructions that I discussed today, and one of them concerns solving cosmological constraints using variational quantum eigensolver, which I did not cover in this presentation. And to conclude, the broader message is that quantum circuit give us not only concrete and operational language for representing quantum state of geometry, but they also opens the door to numerical quantum numerical simulations of large spin networks and to quantum information theoretic analysis of quantum geometry itself. And that's all, I think. Thank you for your attention.
Okay, thank you. Thanks, Grzegorz. I see that we have some questions on the chat, so let's ask. There was a first question from Muhammad. What is the procedure to derive the gravitation propagator?
Okay. Okay, this is quite technical and mathematical question, which I'm afraid I'm not able to answer precisely. So, to be honest, I don't know.
Maybe okay. Maybe you can check later, and we have contact
Mm-hmm.
to Muhammad, and you can let me know, and we can forward the answer. And there is another question from Julian. It was almost at the end. So far, you presented explicitly the quantum circuit for the trivial holonomy, but this in turn has no orientation, so I'm not sure to follow the argument around turning high into uh, hi to the power of
Mm-hmm.
minus 1? Or should I understand that the explicit quantum circuit for the trivial holonomy is for illustrative purpose, but you created a
Mm-hmm.
framework for a general holonomy?
Exactly. Yeah. Exactly. Yeah. This was just for the illustration. This framework is usable for arbitrary holonomy. There is no problem to use arbitrary holonomy. For example, in this place. Mm, oh, Here, the when the holonomy is trivial, so holonomy is identity element, the corresponding quantum state is singlet, and it can be generated using this quantum circuit, X gate, Hadamard gate, and control node. But when holonomy is non-trivial, then this is some other maximally entangled state. So, for example, it could be some, some Bell state or whatever. And then you just need to replace this circuit with circuit that generates this other state. And then in the full circuit, you just replace each generation of the singlet states, you replace with the generation of maximally entangled state that corresponds to the holonomy that you want to simulate. And if you introduce orientation to the links, and you need to swap orientation, and you need to apply inverse of holonomy, you just need to prepare circuits that generate states which corresponds to the inverse of this holonomy.
Mm-hmm. Okay, nice. I hope that it answers the question, Julian, but if you have some follow-up, okay, yeah, thumbs up, so I think this answer was okay. Good. Do we have more questions? Maybe someone would like to unmute and ask. All right, I do not see more questions, so Grzegorz, thanks once again. And
Thank you.
I will just share my slides for last time, just to, yes, just to give some final uh, statements and invite you to the next meetup. So let me share my screen. All right, I hope you can see it now. Just make just turn the full screen mode again. All right. So thank you, Grzegorz, again. I hope that everyone enjoyed the talk. So thank you for your attention. If you are interested in our other activities, let's stay in touch. So you can find all these links on our website as well. So I invite you to follow our social media, subscribe to our YouTube channel, and join our Discord server. We would like to thank once again our strategic partners, R&D, Soundvero R&D, Quantum.io, Onyx, Cogit, AQLab, and FinQubit, as well as our honorary partners for supporting us. If you like our activities, you can donate if you're interested. If you pay taxes in Poland, you can also donate 1.5% of your tax. And with this, we'd like to invite you to our next episode. This time, Michał Stęchły from PsyQuantum, as a quantum software engineer there, will give a talk on July 11th. He hasn't sent me the title yet, but it will be announced soon, hopefully. So the registration will start at the end of May. So yeah, let's please just follow our announcements, and we hope to see you next time on our next meetups. Okay, I will now stop sharing my slides, and I will also stop recording. Okay.